Okay. Good morning, good afternoon, good evening, everyone, and welcome to this technical session on space resource activities. Today we have with us four very distinguished guests with a lot of experience in this topic, and we will be discussing and gathering perspective on the recommendation on space resources within the For All Humanity, the Future of Outer Space Governance, our common agenda policy brief that stated basically to develop an effective framework for sustainable exploration, exploitation, and I'm having feedback here, yeah, and utilization of the moon and other celestial bodies. The framework could include binding and non-binding aspects and should build upon the five UN treaties. So the session will be basically divided into main parts. At the beginning, our four speakers will make an intervention. They will share their insight in this topic, and then we will have a broader discussion where everyone can ask questions. The topic will be divided basically in three areas. We will talk about space mining. Then we will talk also about extracting in situ and in space resources and using them in situ, and finally transporting valuable resources back to Earth and all the technical challenges and implications that it poses. And without further ado, I will pass the word to our first speaker. So today we have with us Mr. John Wroblewskis. I hope that I say the name right. John has a very broad experience in the space sector. He works currently as a planetary engineering specialist at Thales Alenia Space in Bristol. And he has worked in many very known projects such as Rosetta, MVSAT, or recently in the Mars Sample Receiving Facility. He has also experience working for the Ministry of Defense, and he has worked with ESA on the technology development associated to ISRU for oxygen extraction on the moon surface. So John, welcome here to this session. The floor is yours, so you can share your screen, and you have roughly 7 to 10 minutes.
Right, I didn't realise to share. Okay, my name's John Wroblewskis. Is it pronounced Juan? How's your name pronounced? Sorry. But so John Wroblewskis. I'm working at Thales Alenia Space, and we're looking at the technology to extract oxygen from rocks on the moon. So if you think about any rock, and if you do drop a rock on your foot, the thing to bear in mind is that that rock is 40% oxygen. So there is oxygen on the moon, and we are trying to extract it from rock. So yeah, and that's not easy. If I just share now, apologies for this. Can you see the screen?
Yes, we can see it.
Right. So first things first, there's a lot of moon landers planned over the next few years. We've had a few missions already this year. So we had Hakuto RM1, which is a private Japanese mission that wasn't successful. We had the Chinese Chang'e 5 that was successful, a series of very, very successful lunar missions. We had Luna 925, which is the Russian one, which wasn't successful. We had the Indian Chandrayaan 3, which was successful after a failure in Chandrayaan 2. And coming up very soon is SLIM, Smart Lander, for investigating the moon. As well as all of these landers, we have a whole bunch of American landers as well. These are NASA landers in the Commercial Lunar Payload Services CLIPS project. And these are not science fiction, these are real things. So there's a lot of interest in the moon, a lot of activities, and things are moving very, very fast. So where on the moon? Where is resource? As I said, we're looking at oxygen. We're looking at oxygen for mainly refueling. I'll come on to that on my last slide. But the moon has very distinct regions. if I can just quickly talk about the moon, and which I'm focusing on at the moment. The near side is something we recognise. We look at every time we look at the full moon. That is a region of basalt mineralogy. It's a region of pretty dull science. It's all pretty samey and all very well explored. The far side is something that's only just been opened up. The far side, you can see how totally different it is. It doesn't have these volcanic plains. It has a lot more record of the impact craters from the last 3 billion years. And finally, the most interesting part really for science is the South Pole, in that the South Pole is there are some very large craters on the South Pole, the most famous of them being the Shackleton crater. And in the South Pole, what you have is permanently shadowed regions. So inside the Shackleton crater, a comet meteorite that fell 3 billion years ago is still in pristine condition at minus 260 degrees centigrade, because it's very, very cold down there. Also, on the rim of the crater, there's permanent sunlight as well, which is one of the difficult areas of exploring the moon, is that you have 14 days of very, very cold environment that normally destroys any of the landers I mentioned earlier. So at the moment, we're looking at extracting oxygen from pretty much anywhere on the moon. That the process we've got. But on the South Pole, there are activities to extract water, ice, and other hydrocarbons which may have fallen, and it's also of immense scientific interest as well. So that's one of the aspects of the sustain. There's a meeting on Friday. There's sort of speculation that there may be molecules that may have been precursors to life that fell 3 billion years ago that may still be deep freeze on the South Pole. So for our mission that we're doing at Thales Alenia Space, we're looking at extracting oxygen from the moon surface. And the moon surface is very difficult, and our process is very, very difficult. The way to extract the oxygen is that we melt salt, and then we drop in the rock and then do electrolysis. So we're doing electrolysis on molten salt at 800 centigrade on the surface of the moon. And the moon has got some very difficult environments. So that's regolith cohesiveness. The regolith is very, very sticky. Electrostatics, the regolith has many submicron particles and they're easily charged. The gravity is only 1/6 the gravity of Earth. So if we are doing electrolysis, we're not sure about the bubble formation and whether the bubbles will be able to float away from the electrodes to allow electrolysis to take place. Vacuum, the high temperature, corrosive salt, corrosive gases. The lunar surface temperatures, as I said, are very, very hot in the daytime, especially at the equator, and very cold at night. The radiation, the vibration, and there's unknown unknowns. There's so much to explore on the moon that we don't know about. So it's a difficult thing to do. We're currently doing some breadboard testing to determine what can be done and how it might function on the moon. It's not certain that this will work on the moon. So what we're using it for, last slide, is this is the value chain from ESA. We're looking at the production of oxygen on the moon to sell on the moon as well. So we're looking to sell oxygen to anyone on the moon, so they can either take it up to an oxygen to a lunar orbit and then go onwards to Mars, or just use it with fuel brought up from Earth to go up and down from the moon. So we're looking at hundreds of tons per year, at least, depending on essentially how many people are on the moon. So that's my presentation.
Thank you, John. I'm sure that we'll have questions afterwards. Now I want to pass the word to our next speaker. Our next speaker is Professor Vasco Guerra. a professor at the Department of Physics of Instituto Superior Técnico in Lisbon. He's also the head of modeling and simulation activities in reactive plasmas group here at Institute of Plasmas and Nuclear Fusion here in Lisbon. He's also an invited professor in other foreign universities, and he has been working for a long time on modeling non-Euclidean kinetic of low temperatures molecular plasmas. He won several prizes, and he has been recently more involved also on in situ resource extraction and utilization of oxygen in Mars using plasmas. So Professor Vasco, welcome here. I'll pass you the word, and you have the same 7 to 10 minutes to make your first intervention.
Yes, thank you, John, and good morning to everybody. So let me share my screen. Okay. So it's being shared now, yes?
Yes.
Okay. Yes, as you have just said, so I'm working on the physics department of the University of Lisbon, the engineering school, Instituto Superior Técnico, and we have presented this idea to use plasmas for oxygen production on Mars. So you see here, we advanced this in 2018, more or less. We got our 15 minutes of fame on the cover of Europhysics News. And more recently, we were working under the framework of OZIP Ideas program from European Space Agency, and we published this paper, Plasmas for In Situ Resource Utilization on Mars, Fuels, Life Support and Agriculture. And this is basically my background related to space, because my main activity is on plasmas for other applications. So very general statements. When we consider space exploration, we can make this broad distinction between enthusiasts and the skeptics. And of course, here, I guess we are all a bit on the enthusiastic side, but it's good to keep also a bit of the skeptical view. So from the enthusiastic perspective, of course, space exploration is very exciting for many reasons, and among others, the scientific endeavors and developments it brings, inspiration to generations of people, and the use of resources. The science, of course, it's not the main concern or the main thing that comes to mind, but it will also impact our life on Earth for sure. Regarding then in situ resource utilization, which is of course harnessing of resources and exploration sites, that would have to be brought from Earth. Otherwise, the first generation or first things that we want to do are to think on propellants and life support. So oxygen, water, these basic things, building blocks for everything else. By doing in situ resource utilization, of course, we can expect to reduce the logistics of any space mission, and therefore have also extended mission durations. And we need to go through these different steps. So the development of the technology, then prospecting, so looking where on the site this can be done, make a smaller prototype in situ to test and validation, and finally go to implementation. Very often when we discuss ISRU, we focus on the processing, so on what actually has to be done, but it's often undervalued the other parts. So like prospecting, so transport, if we need to mix different conditions and bring everything to the same place, waste treatment and so on. So all these things need to be considered. It is more or less obvious if we just say that we are harnessing resources on site, that this is a positive and a good thing, and this will help us, as I said before, to reduce the logistics of the mission. But in reality, we should always keep in mind the ratio between the mass of the products that are supplied by in situ resource utilization over the mass of the system brought from Earth. And so it is worth to do it when this ratio is typically much larger than 1. So we should compare always a mission that uses in situ resource utilization with a mission that does not use in situ resource utilization, and check if we are on the positive side or not, because also the hardware that we deploy will have a limited lifetime. So it's typically heavy. It must go there, and then it must operate for some time, and then we need to control this mass of the products that we manage to build on site during the lifetime of our hardware. So of course, John just presented Moon, and is of course free to disagree, but I think he will not disagree. He also said that it's a very difficult processing. So the case for ISRU on the Moon is a difficult case. So it's of course interesting, exciting, but to make it, let's say, profitable, to bring this ratio in the correct side, it's very challenging. So the resources may be difficult to access in some cases, and all the processes are very energy intensive, and this is also very challenging. On the contrary, I think the case for Mars is much easier, because carbon dioxide and water are basically readily available. Carbon and oxygen are just on the atmosphere and provide almost unlimited feedstock. And water is also available with a wide distribution, not very deep, 1 meter or so under the surface. And that's what I've been working on and concentrating is on for ISRU on Mars. So again, the atmosphere is essentially CO2, so 96% of CO2. So the oxygen is just there, and that's the first resource that we can think about. The scheme, I don't want you to follow all this scheme. I think most of you know how this goes, but CO2 has to be captured, decomposed, and then O2 is extracted. It can be used for fuel or for life support, and the CO can also be used to produce hydrocarbons, for instance. And there is a twin process that can be done on Earth for the conversion of carbon dioxide to produce green fuels, which is an interesting parallel between a space activity and a real problem on Earth. So other resources just on the atmosphere, the carbon is also interesting, and nitrogen is also interesting. If we have already oxygen and we use nitrogen, we can aim for fertilizers, for instance. And carbon can be used for the synthesis of organic molecules, is also a fertilizer, and to manufacture carbon structure. So quite interesting and diverse options on Mars. And to finish this intervention, I'd like to note that the requirements for transportation of crew, so if we think on manned missions to Moon and Mars, are very different. This seems a sort of obvious statement to make, but it's important to keep it in mind. So, of course, the mission to Mars is much longer. We need to consider that, all the environmental control and life support systems must be fail-proof for a long time. There are no abort options. Once you go, you need to go and wait more than 1 year to return. The mass of everything that needs to be considered is much bigger. The effects of microgravity radiation in humans for much longer time. So it's a very different mission. It was implicit also on my previous slides that the case for in situ resource utilization on Mars looks more feasible and with a greater mission impact on the long run. So I think it's something worth to explore and keep in mind. And also a word of caution that the excessive use of the lunar paradigm for Mars mission is to some extent inappropriate for these reasons that the missions are really very different. And I want to acknowledge that all these ideas are discussed in detail in a very recent book from Donald Rapp on human missions to Mars, where I also draw inspiration for this presentation. And yes, with this I will finish my first intervention.
Thank you, Vasco. Thank you for your insights here. I'm sure that we'll have interesting discussion afterwards. Now I want to pass the word to our next speaker, Joost van Horschot. I hope I said the name right. Joost is the founder and CEO of Mana Electric. He studied economics and business at Utrecht University, but then also master's space studies at ISU. He has worked in many different companies before, and now he's in charge of Mana Electric. Mana Electric is a new space company focused basically on using in situ resource utilization technology to produce energy resources both on Earth and in space, and they have already many purchase orders, but I'm sure that we will hear more about that. So Joost, welcome. Same, you have 7 to 10 minutes for your first intervention.
Sure. Thank you so much for the kind introduction. Yes, I come from a little bit of a different angle than the previous speakers, of course, because yes, I have the economics background, and I've been an entrepreneur for more than a decade now, and I always look for business cases, because business cases are what make businesses run, and we all want to make business cases to not just rely on the public funding that is available in the space industry, of course, which is essential, but it's not how we get there in the long term. And I think where we really started as Mana was with the realization that at some point humanity will become multiplanetary, and it is important also for the survival of humanity to become multiplanetary. So why not help to speed this up and do it in a way that it also results in benefits for us here on Earth? And we really started with the analysis that, yes, oxygen for fuel and propellant is of course key, also the hydrocarbons. But in reality, to get to those fuels, what you often see in the graphics is this magical arrow called power. And the reality is that to live on the moon, to live on Mars, to live anywhere in space, electrical power is extremely important, and it's as important for living on the moon or on Mars as food and shelter have been for human survival on Earth. We were able to go to the Americas or explore across the world without power, but in space you cannot do this without power. And this is really where we decided to start off with the business. Is power is the most essential thing, in our opinion, to get humanity to beyond Earth orbit. And let's also be real that if you want to do any significant quantity of resource utilization on the moon, but also Mars, you need significant amounts of power, not kilowatt scale, but really megawatt scales of power, if you want to produce the volumes of oxygen and propellant that you need to make a business case also for these other cases. And so really, how will we power those resource utilization activities? That was really where we started from. And in our opinion, we should, of course, use in situ resource utilization to produce the power resources that you would need on the moon and on Mars. And this has been what we have been working on at Mana primarily, is to use our ISRU technologies to produce solar panels, to produce all the required components in order to be able to provide power sources for future space activities. And we do this primarily for our lunar product with the Luna Box. So this is a machine capable of producing more than 1 megawatt of solar panels a year. That is really our long-term ambition, to develop this machine and to basically use the local resources to produce these solar panels. So we created the company in 2018 and have been working on this since. And making good progress towards this. Of course, our first payloads that we are working on is really proof of demonstration that it is possible to produce the components for solar panels. But of course, we have to take the stepping stones that are required to get there. Now, I think what's important is that we don't think we can make a business just off of the space business, at least at the moment, because everyone has wildly different timelines on when we will actually have ISRU activities and economic activities on the moon, even longer on Mars. So our master plan always resided on making sure that we first develop these technologies for space applications, for terrestrial applications, and that we make sure that these technologies also make sense on terrestrial applications. But it allows us to build a business that will allow us eventually to do the same activities on the Moon or Mars. So really how we have functioned as a company is we do R&D contracts, early TRL R&D contracts from with the space industry, and this enables us to develop terrestrial products. So we have a wide array of space projects that we are working on, from extracting silicon from lunar regolith, also environmental chambers for lunar and Martian simulation, producing energy storage systems from using ISRU, producing iron, and also looking at solar arrays. And this has led us into basically supporting the R&D for terrestrial product lines. So today we have 3 terrestrial products, primarily on solar panel manufacturing, solar cell manufacturing, and also silicon manufacturing. And we've been fortunate enough that we have today more than 100 million euros in purchase orders for our different product lines. And I think this is important because like this, we can build a business that will allow us in the long term to have the technologies ready to do something similar on in space without being so dependent on these long-term R&D funding, which is somehow the backbone of deep space exploration at the moment. Yes, so thank you very much. Happy, of course, for the discussion to come.
Yeah. And thank you, Just, for the presentation. Also very interesting and forward-looking. And finally, our last speaker for today, it's Julien Alexandre Lamami. Julien studied in École Centrale de Lyon, and he did his PhD in MIT in space system engineering. He has a lot of experience working in space sector, both in space agencies at NASA, but then also in industry. And right now he is the CEO of iSpace Europe in Luxembourg, also a new space company. So welcome here, Julien, and the same, you have said 10 minutes for your first intervention.
Thank you. Can you hear me okay? Sound check?
Yes, I can see the slides.
Okay. Yeah, good morning. Thank you. If you can see me, you can see a moon background, moon picture in the background. That's a picture that our first mission took this year. So John, the first speaker, mentioned the Hakuto R mission. That was an iSpace mission, our first attempt to land on the moon. So we launched on a SpaceX rocket last year and attempted our landing on the lunar surface this year, and we'll try again end of next year. So that's iSpace, the overall company. Here I'm going to focus on iSpace Europe, the subsidiary of iSpace located in Luxembourg. And we heard about a lot of ISRU plans, space resources plans, and I want to talk about the first step on how to get there using this little robot that you see in the picture. For background, iSpace Europe, what we do basically lunar robotics, so surface mobility, but also data analytics tools. We're located in Luxembourg City, and there we have all our engineers designing lunar robots, testing them in our lunar yard facility, assembling and testing the actual flight hardware that you can see, and also doing the operations in our small mission control room. So we can do everything from designing, building, testing, and operating lunar robots from Luxembourg City, which is quite unique. We're a team about 35 people, 2/3 engineers, 20 plus nationalities. And so with this great team, we responded to an opportunity from NASA that came out now 3 years ago to collect regolith and basically sell the regolith to NASA. So regolith is the lunar soil. It's the basic resource that Mana Electric will use to produce solar panels, and that Thales will use to produce oxygen. The first step there is to collect it and see how a commercial company might claim ownership over that resource. That's exactly what NASA wanted to test. So they put out this request for quotation 4 companies were selected for this contract, which is very symbolic. Only $20,000 or so were allocated for the total of the 4 awards. We, iSpace Europe, won one of the 4 awards, and we plan to execute that next year. And you can see a little picture of the robot we used to do that. We responded to this bid for 2 reasons. One is we appreciated the effort by NASA to kind of accelerate the discussion on regulations surrounding space resources and the commercialization of those space resources. And also, being in Luxembourg, we saw the opportunity to test the legal framework that Luxembourg had put together in 2017. So a year after the US, Luxembourg was the second country to establish a law on the commercialization of space resources. So we saw it very fitting to use this NASA opportunity to test the law, and possibly being the first company to put this law to the test. Which is what we're aiming to do. So the contract itself, as I said, is very symbolic in terms of financial value, and it's basically collect at least 50 grams of regolith, take a picture, and prove that you have 50 grams, and that's it. We hold the regolith until NASA decides to come and pick it up if they ever want to. So from NASA's perspective, it's very much a legal test of the regulations. Once we were awarded this contract, what we saw is a great opportunity to involve the actual experts in the field into this lunar mission. And we found this great company, Epiroc, one of the leading manufacturers of mining equipment for subsurface drilling, and they were very interested in doing this small symbolic mission with us. So we partnered. We have a commercial partnership together. We also now have a long-term collaboration agreement with them to think about future missions. But on the first mission that we'll do, which will perform this space resource collection for NASA, the actual extraction system is completely designed and manufactured by Epiroc, and so they're doing for us a little shovel scoop that's about a couple hundred grams, whereas the standard product line that you can see here is more in the order of several metric tons. But that shows that we're making progress in getting interest from the actual terrestrial industry that Joost was referring to, in thinking about the moon and potential business there and practices. So to finish, a little video of what it might look like once we're on the moon. So this is not the moon; it's our lunar yard in Luxembourg. And we're controlling this rover in flight-like conditions from a simulated mission control room. So it's a very simple rover, about a few kilograms. And you see in front the scoop that's folded, so it's in a stowed position. And our operators are looking at the feed coming from the camera, which you can see was just above the scoop. And here we're just practicing the collection activity that we'll perform on the moon. So very simple. We collect, we hold until NASA decides to come and get this at some point. This mission will launch end of next year. So it will be the second Hakuto-R mission. The first one was just a lander with a number of payloads. It had a rover, but it was a customer rover from Dubai, from the Mohammed bin Rashid Space Center. The second mission has a rover, but this time it's our rover, made in Luxembourg, 100% made in Luxembourg, with the screw from Epiroc and another payload from another customer. So I hope to have this same discussion in about a year from now, and we can discuss how we actually did it as opposed to how we plan to do it.
Thank you, Julian. Thank you for your presentation and also this very nice video. So thank you all for your presentations. Now we have a bit of time, roughly 20 minutes, for an open discussion. I would like to encourage you also to interact, so you can also ask questions among yourselves for what you have seen. But I would like to start with the first question on how far do you think we are from really utilizing ISRU? We have some experiments like MOXIE. We see here maybe for moon missions, or also some demonstrators on some key technologies. ESA's also working on a pilot plant. But how far? When do you think that this is gonna start really becoming something recurrent in space missions? So I don't know who wants to start, but maybe let's start with the moon, which looks closer. What are your thoughts on this? Maybe John.
It depends on how much money is really spent on the moon exploration. At the moment, there is a great deal of interest getting to the moon, and a great deal of money being spent in Europe, as seen by the presentations today, and then also loads more, 10 times as much being spent in NASA, and then the Chinese and even the Indians. So my estimate at the current rate, about 15 to 20 years, but at the moment, and coming back to Jost's point about business cases, we've got to establish a business case that producing oxygen on the moon, for example, is cheaper than carrying oxygen from the surface of the Earth to the moon. But there may be a case when the permanently shadowed regions on the South Pole are explored, that something much more valuable, much more easier to extract is found on the moon. And that may sort of spark a gold rush, really. The scientists are worried that a lot of the science may be lost on the South Pole if all the hydrocarbons are used, and they would move towards having a moratorium on the North Pole. There are some permanently shadowed regions on the North Pole as well, but the South Pole could be very, very busy in 15 years' time. And then the other aspect is planetary protection. No one's mentioned planetary protection as well. So as you mentioned, I was involved in the Mars sample receiving facility, a facility which for when you would bring the samples back in about 10 years' time. But planetary protection regulations would be something that may prove to be a non-technical issue for ISRU, and may be bypassed by a high-value individual setting up a spaceport in Kenya, for example, or another country setting up a spaceport in somewhere like Djibouti, where they can get access to cheap launches with different regulations. But so the regulation is for me, doing all this demonstration of the technology, there's something called the TRL Valley of Death, where you have these great technologies, but they die before they can get to high TRLs, mainly because of these non-technical issues.
So it's understand that there are mainly three constraints: technical, funding, and regulation for these to move forward. I don't know if anyone also has some thoughts on utilization of resources in the moon and maybe limitations and challenges. We see that access to space is becoming much more affordable, and this is certainly a driver of this. But I don't know, what's your experience also, Julian, on this? What are your thoughts? Because you have a clear roadmap here.
What I think is exciting is that iSpace has started this transportation service 6 years ago, and in a span of 6 years, we're seeing a lot of companies being created downstream of transportation for the moon. So Mine Electric is an example, and there's others that are looking at other aspects of the value chain for moon. communications, but also space resources. And we've been approached by a few companies who intend to also demonstrate, pilot plants on the moon. And if they could, yes, there's always, a question of budget, but within the decade. So that's what I'm excited about. Is we're seeing a lot of people already downstream thinking of how to use commercial lunar transportation and the lower price and accessibility to develop new businesses, as you also were saying, new technologies, start small, and maybe replicate what we did with Epiroc, getting the interest of existing large industry also in Earth to sponsor some of the first steps until we reach, the sustainable business model that John was referring to. Okay,
that's clear. Now, and also thinking more on Mars exploration, Vasco, how far do you think this is? When do you think that certainly a driver for ISRU development in Mars, it's going to be eventually in the future when an eventual manned mission goes there and all technologies that will be needed by then? What are your thoughts on that?
Yeah, so of course Mars has MOXIE is there, so there is already something working. It's of course a pilot. It's a small scale, but it's the important starting point. Yeah, so that's the first observation. Though it's already operating ISRU system on Mars. So then it's the question. How to scale it up, how to bring it to the next level. So that's one direction. And it was mentioned already by John. Okay, that's basically how much money you put in and what are the political decisions to pursue that effort. Because the roadmap, I think it's more or less clear. I'm not saying that it's easy, but it's more or less clear on how to do it. On the other side, so the complementary direction is to go for the other resources. So to do the pilots and the demonstrations on the other resources. And of course, the key point here is hydrogen at some point. So to bring hydrogen into the game. I was also on the enthusiastic view saying, yeah, but there is plenty of water on Mars and it's more easily accessible and so on. But that's, I would say, the bottleneck for the moment to understand how to move on Mars is to assess how difficult it is in reality to touch the ice that is under the surface. Okay, the optimistic view is not very far. It should be possible to bring it. This prospection of where to make it is also not very complicated because it seems to be available quite broadly on the surface. But this is, I would say that this second complementary route to go for the water and the hydrogen would be the important next step on Mars, because then with oxygen and the hydrogen you can do pretty much everything. And I'm thinking of course, human missions are exciting for us, and this inspiration part, and the vision of becoming a multi-planetary species. But on a first step, I think propellants there let's put it in a common sense language, to have a gas station on Mars to refuel, that would be already a huge step. And so I think this exploration of the water and accessing the hydrogen would be an important next step. And I cannot put a timeline, but maybe the same 20 years that were mentioned before. I don't know.
Oh, it's certainly very difficult to predict. But now you're touching upon 2 points, which is business case, and now you mentioned hydrogen. And we're talking here mainly about in situ resource utilization, but there are also extraction of resources that are rare, very rare on Earth, but are not that rare in other celestial bodies. And one resource that has been talked a lot about is tritium, at the end hydrogen-3, which is a fundamental element for nuclear fusion and has other applications. And apparently the moon has a higher density, or it's more accessible than here on Earth. And I want to see What are your thoughts on this? Do you believe that there are resources, relatively accessible resources that have strong economical potential and can accelerate these space resource utilization or space mining? What are your thoughts on this? I don't know who wants to go.
Yeah, I can jump on this one. Look, I think the risk with looking at like tritium or something like this is that we are talking about also an unknown technology with fusion. So as long as fusion has not been proven to work effectively, then it's still a blur if tritium mining would make sense. Look, in our opinion, the starting point for ISRU really needs to be ISRU for space applications, because this is, let's say, easier to do than start bringing resources back to Earth, in our opinion. Now, there for sure are valuable resources in space, and let's be clear. Let's look at, for example, battery technologies. We have cobalt that we like to use in batteries for very good technical reasons, and we don't use it, or we try to eliminate it now, mainly for geopolitical reasons. So if you can source materials which do not have those geopolitical implications, obviously it's attractive. I think also dropping the prices of certain raw materials that have very good engineering applications is very attractive for continuing to grow in general the economy of humanity, let's say. So that's where I think the attractivity of space resources can play in the long term. If you do look at platinum group metals, they are very expensive right now, but they have tremendous properties that we would love to use. If you talk to any engineer, they would love to use platinum for almost every application, but it's just too expensive, right? So and we've seen this in the past happen also in history. Look at, for example, aluminum at some point was more valuable than silver or gold. There's the famous story of Napoleon eating with aluminum cutlery, right? Because it was so valuable. And now aluminum price is okay. It's still more expensive than iron, but it's a commodity, right? So when you can bring certain elements back to or drive the price down to commodity level, obviously it will have an impact on economies here on Earth. But I think in the long term it has a positive impact. In the short term, yes, it will put certain people in tough economic positions, but in the long term it has economic value. Maybe I just wanted to address the timeline, which was addressed previously by the other speakers, because I tend to agree with the timeline that is mentioned, but I think there's one disclaimer, and I think that's that we are underestimating the speed of acceleration that we are at right now at the crux of happening. If we look at the number of commercial landers that are going to the moon, iSpace has one next year. There is 2 or 3 other companies that also plan to land commercial landers next year. We have SpaceX with their Starship making progress. Now, we don't know in what kind of timeline, but if these innovations start to happen, I think it will drive down the cost of getting to the moon and eventually also to Mars. It will drive that cost down significantly. And then the capital cost of going in, and trying to do things on the moon and trying to do things on Mars will go down significantly. And I think that's a real big shift that is happening that will really enable mission. Look, we are, for example, looking at a small mission to the moon, and it will cost 50 million euros for, let's say, 10 kilos to the moon. That price, I expect, in the next couple of years could really be driven down to half, if not less than half, just because of the success that I hope and expect will happen in the next years. And I think that will be a real accelerant on the getting to the moon. Yes, sorry for the long.
No, thank you, Jules. I think it's very good insight here. I don't know if anyone else wants to comment on this topic, but we have, yes, please, John.
Yeah, basically, in short, sustainable business case that Jules mentioned in his talk. It's if there's a business there, if there's something valuable to extract, then things will accelerate. Mentioning cobalt, one thing we haven't mentioned is asteroids as well. So Vasco is exactly right. The moon is not, it's easier than, it's easier than some place to get to. But if you were to, because of the gravity well on the moon, if you were to get to the moon and want to bring things away from the moon to Earth, it's easier potentially to go to an asteroid than a moon if there's an asteroid that's found with a valuable resource. Again, you got more difficulties there. But again, asteroids are being actively explored at the moment. Much knowledge has been gained from the asteroid missions. Sample returns from Hayabusa, the Japanese mission, and OSIRIS-REx is enhancing our science of exactly what is in the asteroids. And it may be the case that some of the resources that are not on the moon could be augmented by the resources that are on asteroids, hydrogen and carbon, maybe.
Yeah, that's also very relevant as well. We have a question from the audience on YouTube. I'm going to read it out loud and then you can pick it up. The question is if you think that some structure for property rights for in situ resource should evolve prior to utilization. So developing more the legal framework, perhaps on property rights, on ownership, before, of course, moving to utilization. What are your thoughts on this? Because it's a very relevant topic, and I know you have already touched upon that Luxembourg and the US are moving forward. They have already some legislation on this. What are your thoughts on the parallel evolution of the technical side and the legal side here, and ownership?
My thoughts are, I tend to read some science fiction as if you look towards missions in the long term, then it is possible that if you did have a sustainable colony on the moon or a sustainable colony on Mars, they would be fully independent from Earth. This is maybe 50 years in advance, and some science fiction books have been written about this. But in terms of the legal framework on the moon, at the moment it's in my view, and I'm not a legal expert, it is in a position where it's not as strong as it could be. Hence this talk really. But say legal structures on the moon, MySpace are doing it with their contract to ESA for the 50 grams of regolith. It's a step in the right direction, but we do need if we do want a legal framework on the moon, then we do need a much stronger legal framework on Earth to enforce it really.
Okay, thank you. That's clear. I don't know if anyone else also wants to reply on this topic. No, so I think that we are coming. Yeah, please go ahead. Just.
Yeah, look, I think none of us are legal experts, so I wouldn't also want to comment on legal aspects, but I think what's clear is that we need to have the regulations in place on time, otherwise it will be a Wild West. And I think putting in place too restrictive legal regulations, as John mentioned as well, at some point, I think people will get around it at some point. So it has to be a smart regulation that makes sure that economic operators can do the work that they need to do, while still being in the net good and net positive for everyone. That it's not just let's say some billionaires who profit from it, but that it's really the humanity which profits from it. And let's be honest, this is more a job for the UN than it is for us sitting here to undertake. But I think it's important that some serious steps are taken in the very short term, because yes, it could be a 15-20 year horizon, but it could also be a 3 or 4 year horizon. And with the way that some of the developments are going, it could be that flying 50 tons of mass to the moon could become very accessible in the next couple of years. And if the regulation is not there yet, then it will be the Wild West. And that's not in anyone's interest, I would say. So I think it's behind, in my opinion, as far as I am aware. Again, I'm not an expert, but it needs to really start catching up, because let's say with some of the developments happening, Starship and also the commercial landers, I think it's really speeding up, and you will have people extracting resources, or as Julian mentioned, testing the boundaries of the laws, right? With actually grabbing regolith and to some extent claiming ownership of this. If there's no rules, the industry will make their own rules, and that's I think not the proper way.
That's also a good point. So I think that we are coming to an end for this session. I don't know if anyone else wants to make a final remark, final comment here. But if not, I would like to thank you all for your very valuable insights and for your time. And I hope that this discussion was useful and that we see an evolution on this topic in the future. Thank you very much, and see you soon. Bye-bye.
Bye.
Thanks, bye.
Bye-bye.